Hello students, welcome to EPG Pathshala. I am Dr. Aditya Saxena from Central University of Haryana, Department of Physics. Today, we are going to discuss about the module Postulates of Quantum Mechanics under the paper Quantum Mechanics 1. So students, let us see what all we are going to learn in this module. To begin with, we will learn the state of a physical system in terms of the state vector in Hilbert space. We'll know how a Hermitian operator acting on a state vector gives us the information of a physically observable quantity in terms of various eigenvalues. We will learn the definition of expectation values of the corresponding operator in the state. We will know the properties of quantum mechanical operators and of canonically conjugate operators. We will know the time evolution of a quantum mechanical state vector. We will learn some important properties of representations, basis of Ket and Bra state vectors, and unitary matrices. Now, let us understand how we are going to develop this quantum mechanical formalism. We have already developed the properties of vectors and operators in Hilbert space. An underlying mathematical framework of quantum mechanics. Now, in this module, we will present the basic postulates using Dirac notation in a form appropriate to the Hilbert space formalism of quantum mechanics. The next section is devoted to studying the mathematical properties of representations of the Ket and Bra vectors and operators and unitary transformations from one basis to another basis. State vectors and observables of a physical system. Now we will be discussing the different postulates that are there for the mathematical formalism of quantum mechanics using state vectors and observables of a physical system. Postulate 1. Each state of a physical system is represented by a vector, that is Ket vector A, referred to as a state vector in a Hilbert space. To this postulate is added the principle of linear superposition, according to which if Ket vector A1 and Ket vector A2 represent the possible state vectors, then a linear combination of these two state vectors, that is Ket vector A, is given as alpha times Ket vector A1 plus beta times Ket vector A2 is also a possible state, where alpha and beta are arbitrary complex numbers. So here we see that if we have two state vectors, then using a linear combination of these two state vectors, we can write another state vector, which also represents a possible state of the system. Now, let us come on to the second postulate. Postulate 2 states that for every dynamical observable A, like energy, momentum, etc. of the system, there exists a Hermitian operator in Hilbert space. Here, what we mean by dynamical observable is the physical quantity that is measured in such a system. Expectation values measurement postulate. Now, continuing postulate 2, we see that the only measurable values of a physical observable are the various eigenvalues of the corresponding operator. Each of the eigenvalues of the operator, say operator A, has associated with it a vector represented by ket vector AK, so that operator A acting on ket vector AK is equal to eigenvalue AK into the ket vector AK. Eigenvectors corresponding to different eigenvalues are orthogonal, that is, bra vector AI ket vector AJ is equal to 0 for all I not equal to j, and also normalized, that is, bra vector AK ket vector AK is equal to 1. So here what we see is that the operator A that acts on a state vector gives the corresponding eigenvalues associated with that eigenvector or the state vector, where these eigenvalues are the measurables or the observables of the physical system. Also, we see that it is convenient to define the state vectors such that they are orthonormal. That means that if you have a bra and a ket state vector together, then if they represent different states, then their product comes out to be 0. And if they represent the same state, then they are normalized to unity. Now we come on to postulate 3, that is the measurement postulate. If the measurement is made on large number of identical systems, each characterized by a state represented by a normalized ket vector, then the average value, that is, the expectation value of the operator, is defined by average value of operator A is equal to bra vector psi operator A acting on ket vector psi. So here the state vector or the eigenvector psi is normalized, which means that either it will be normalized to unity or it will be normalized to the number of particles that are present in the system. Normally, we normalize all the state vectors or the eigenvectors to unity. Quantum mechanical operators. Now, continuing in postulate 3, that is the measurement postulate, we see that in case the ket vector psi is an eigenvector of the operator A, that is, ket vector psi is equivalent to the eigenvector AK, where operator A acting on eigenvector or the ket vector AK is equal to eigenvalue alpha k times the ket vector AK, then the expectation value or the average value of the operator A is equal to alpha k, that is the eigenvalue of the state. Now, if the ket vector psi is not an eigenvector of the operator A, then the ket vector psi can be expanded in terms of the eigenvectors ket vectors AK of the operator A, that is the entire set of the eigenvectors AK of the operator A, which form a complete orthonormal set of Hermitian operators. That is, that they are orthogonal to each other if they represent different states of the system, and they are all normalized to unity if they represent the same state of the system. We then express the average value of operator A, that is the expectation value of operator A, as bra vector psi operator A ket vector psi is equal to summation over k square of the modulus of bra vector psi ket vector ak into the eigenvalue alpha k. This equation gives us the result of a large number of measurements under identical conditions. We postulate that the probability of finding the state ket vector ak is p operator ket vector ak, that is the probability operator acting on ket vector ak, is equal to the square of the modulus of bra vector ak and ket vector psi. Then now we come on to the next postulate, that is postulate 4. Quantum mechanical operators. This postulate discusses the quantum mechanical operators and how these operators interact with each other. Canonically conjugate operators. Now, coming back to postulate 4, let us consider a dynamic variable, say the Hamiltonian of the system, which in classical mechanics represents a function, or in classical mechanics the Hamiltonian is a function of canonically conjugate variables. Now, the corresponding picture in quantum mechanics is that the Hamiltonian in quantum mechanics is the corresponding quantum mechanical operator of the system and is obtained from the dynamical variable in classical mechanics by replacing the canonically conjugate variables by the corresponding quantum mechanical operators. That means that the canonically conjugate variables of classical mechanics now get replaced by the state vectors of quantum mechanics which define the system. We can take an example over here and let us consider a Hamiltonian of a linear harmonic oscillator. This Hamiltonian of the linear harmonic oscillator in classical mechanics is given by h is equivalent to h as a function of x and p, where x and p are the canonically conjugate variables, and is given by px square by 2m plus half kx square, where we see that x is the position coordinate and p is the corresponding canonically conjugate momentum coordinate. Now, according to the postulate, we have that the quantum mechanical operator corresponding to the Hamiltonian H as defined above for the linear harmonic oscillator in classical mechanics is obtained as operator H is equivalent to operator H as a function of operator X and operator Px, where Px represents the X component of the momentum, and this operator H, as in the Hamiltonian operator, is equal to the X component of the momentum times whole square, that is Px square upon 2m, where m is the mass of the system, plus half k operator x whole square, where k is the restoring force constant, or the constant which gives us the potential energy of the Hamiltonian, and where the operator x and the operator px are the corresponding operators as defined in quantum mechanics vis-a-vis the canonically conjugate variables as they were defined in classical mechanics. Heisenberg commutation relations. Postulate 5. Any pair of canonically conjugate operators satisfies the Heisenberg commutation rules, which are given as follows. The first rule is commutation of operator Qi and Qj is equal to 0. The second commutation rule is commutation of operator Pi and Pj is equal to 0. And the third Heisenberg commutation rule states that commutation of operator Qi and Pk is equal to IH cross operator I delta Ik, where delta Ik is a delta operator or the delta function which is equal to 0 for I not equal to k and is equal to 1 for I equal to k, while the operator I is the identity operator. Here, in these three commutation relations, the operator Qi represents the generalized coordinates corresponding to Qi, while the operator Pi is the operator corresponding to the generalized momentum Pi, which are all canonically conjugate to Qi. Thus, in this abstract formalism, the commutation relations like commutation of operator x and operator px is equal to IH cross may be regarded as a postulate not to be derived. This forms the basis of quantum mechanics. Time evolution of a state vector. Postulate 6. The time evolution of the state vector is governed by the Schrödinger equation, that is, the time-dependent Schrödinger equation, which is given as IH cross d by dt ket vector psi as a function of t is equal to Hamiltonian operator as a function of t times ket vector psi as a function of t, where operator h as a function of t is the Hamiltonian operator associated with the total energy of the system, and h cross is equal to h by 2 pi, where h is the Planck's constant. Now we come on to the representations, bases, and the unitary operators. We have seen that any vector in an n-dimensional vector space can be expanded in terms of the orthonormal basis having the basis set ket vector ui n. Thus, we can write if we have any two state vectors ket vector x and ket vector y as arbitrary vectors, then we can expand these vectors in terms of the orthonormal basis set uin, and this can be given as ket vector x is equal to summation over I going from 1 to n, where n denotes the n-dimensional vector space, xi times the ket vector ui, where xi are the coefficients or the eigenvalues. Similarly, the ket vector y is defined as or can be expanded in terms of the orthonormal basis uin as ket vector y is equal to summation over I going from 1 to n yi ket vector ui, where yi are the coefficients or the eigenvalues corresponding to the arbitrary vector y. Representations, and bases. Now, if supposing we have an other vector, ket vector z, such that this ket vector z can be expressed as a linear combination of the ket vectors x and y and is given by the equation ket vector z is equal to alpha times ket vector x plus beta times ket vector y, where alpha and beta are the coefficients which may be complex variables, and then we can also write the ket vector z in terms of the orthonormal basis UIN, and the ket vector z can be expanded in terms of this orthonormal basis by the relation that is given as ket vector z is equal to summation over I going from 1 to n zi times ket vector ui, where zi are the coefficients or the eigenvalues corresponding to the ket vectors ui for the ket vector z. Now, if the ket vector z satisfies these two above mentioned equations, then we can write the coefficients zi for the ket vector z as zi is equal to alpha times xi plus beta times yi. Also, the bra vector x, ket vector y is given as summation over I going from 1 to n xi star times yi, where xi star is the complex conjugate of the coefficient xi. These relations suggest that in place of the abstract vectors ket vector x, ket vector y, and so on, we can even deal with their expansion coefficients or the components, where the components of x are given as x1, x2, and so on till xn for an n-dimensional space, and the components or the expansion coefficients for y are given as y1, y2, and so on till yn, where n again represents the n-dimensional space. These expansion coefficients are called the representatives of the vectors. These representatives, unlike the vectors, depend on the basis that is chosen to represent them. That is, that these representatives of the vectors are attached to a particular basis and are not independent of the basis in which they are defined. Representations and bases. Here, let us see that with respect to a given basis, how do we represent various terms. So, the representative x corresponding to the vector ket vector x is unique, which is represented over here by the representative x, and in the representation defined by the basis ket vector uin, where n denotes the dimension of the space or the system being considered. The basis vectors are represented by the representatives u1, u2, u3, and so on till un, where the representative u1 is equal to 1, 0, 0, and so on, and the nth element is also 0. The representative u2 is given by 0, 1, 0, 0, and so on till the nth element, which is also 0, etc. Now, one could also express the representative x of the vector ket vector x in the form of a column matrix, and this is given as representative x is the column matrix x1, x2, x3, and so on till xn. Similarly, if we want to represent a bra vector, then the representative of the bra vector X is represented by a row matrix X dagger, where the representative X dagger is a row matrix given by x1 star, x2 star, x3 star, and so on till xn star. The scalar product is simply given by the matrix product x dagger y. Change of basis. Let us now find the relationship between the same set of vectors and operators given in different representations. So, for this, let us consider two different orthonormal bases in the Hilbert space that are given by the orthonormal basis UIN and UI prime n, where n represents the n-dimensional space. Now, since both these orthonormal bases are sets of complete vectors, that is, both these orthonormal bases are complete sets, the vectors of one set can be expanded in terms of the vectors of the other set. So, if we want to represent the orthonormal basis ui prime n in terms of the other orthonormal basis uin, then we can do that through an expansion that is given by ket vector ui prime is equal to summation over j going from 1 to n ket vector uj times sji for all I going from 1 to n, and where n is the dimension of the space. Here the expansion coefficients, that is sji, can be regarded as the matrix elements of an n cross n matrix. That means the matrix S represents an n cross n matrix whose elements are represented by the expansion coefficients Sji, which transforms the representation of the orthonormal basis uin to the representation of the orthonormal basis ui prime n. This can be understood in this manner, that supposing in our normal coordinate system, if we have one set of coordinate vectors, then we can make a transformation from one coordinate system to another coordinate system by defining a transformation between the coordinate vectors of one coordinate system and the coordinate vectors of another coordinate system. For example, we can define a transformation between curvilinear coordinate system and spherical coordinate system, or even a cylindrical coordinate system. And for each of these coordinate systems, we can define separate coordinate vectors and we can define the corresponding transformations between these vectors. So the orthonormal basis uin and ui prime n can be considered as some kind of basis which represents some kind of coordinate system. Unitary matrix. Now let us take the scalar product of the ket vector uj. So we get the Punch coefficient sji as defined by the relation sji is equal to bra vector uj ket vector ui prime. Now, using the orthonormality of the set, that is the orthonormal basis set ui prime n, we have ket vector uj prime bra vector uj prime ket vector ui prime is equal to delta ji. This is equal to summation over k going from 1 to n bra vector uj prime ket vector uk bra vector uk ket vector ui prime, and this is equal to summation over k going from 1 to n s kj star s ki is equal to s dagger s ji is equal to delta ji, where s is the expansion coefficient, and over here we see that in the above relation ket vector uk bra vector uk gives us a 1 or a unity, and that since we have an orthonormal basis set, therefore wherever the elements or the coefficients of expansion represent different states, there they will always return a delta operator, such that if the states are the same, then the delta operator will return unity, and if the states are different, then the delta operator returns a 0. Also, Skj star represents the complex conjugate of the expansion coefficients Skj, and S dagger represents the adjoint of the operator S. Now, here we have also used the closure property of the basis. Similarly, if we also use the completeness property of the basis, we get bra vector uj ket vector ui is equal to delta ji is equal to summation over k going from 1 to n bra vector uj ket vector uk prime bra vector uk prime ket vector ui is equal to summation over k going from 1 to n sjk sik star is equal to ss dagger ji. So here Sjk and Sik star are the expansion coefficients, where Sik star is the complex conjugate of the expansion coefficient Sik, and S dagger represents the adjoint of the operator S. From this, we see that using the completeness property and also the property of closure, we reach the result that S dagger S is equal to I is equal to S dagger, where S dagger is the adjoint of the operator S and I is the unitary operator or the unitary matrix. So in case I is the unitary matrix, then S and S dagger represent the matrices of the expansion coefficients, where S dagger is the adjoint of the matrix of the expansion coefficient S. Transformation laws of operators. Note that the linear transformation ket vector y is equal to operator A acting on ket vector x in the matrix representation is written as y is equal to ax. In the U representation, where U is the set of coefficients u1, u2 and so on till un, where n is the dimension of the space, and where uk is a column matrix representing the basis vector, so that U is an n cross n matrix. From the orthonormality of the basis, we require that U dagger is equal to summation over I going from 1 to n ui dagger is equal to I, where I is a unitary matrix. Thus, we see that U is a unitary matrix. Now, let us look at another representation. In the representation U prime, where we can define the new representation U prime as some representation U times S, where S are a matrix of expansion coefficients. So we can write down U prime is equal to U times S, and we have Y prime is equal to A prime X, where X is equal to S X prime, and so we have S Y prime is equal to A S X prime, or the Y prime can be given as Y prime is equal to S dagger operator A S X prime, where S and S dagger are the expansion coefficient sets and S dagger is the adjoint or the complex conjugate of S. On comparing all these equations, one finds that A prime is equal to S dagger operator A S. This is the transformation law for operators under change of basis. So in this manner, through the various equations discussed above, we can define linear transformations from one basis set to another basis set through the operations that have been discussed above. And using these different transformation laws, one can go from one basis set to another basis set, and also one can construct a new basis set using a linear combination of the existing orthonormal basis sets. So students, now let us summarize that what all we have learned in this module. So first of all, we learned how we can represent the state of a physical system in terms of the state vectors in Hilbert space. After having learned how to do this, then we went on to know how a Hermitian operator acting on a state vector gives us the information of a physically observable quantity in terms of the various eigenvalues. Now, here it is important to understand that the physically observable quantities are the quantities that one can actually find out in a quantum mechanical system. And these physically observable quantities are given by the corresponding eigenvalues which correspond to a particular state vector. So over here we learned how using a Hermitian operator, which when acting upon the state vector gives us this physically observable quantities in the form of the eigenvalues. Then we also learned the definition of the expectation values of the corresponding operator in the state, where we saw that the expectation value is actually the average value of the observable or the state vector. After that, we also learned about the properties of the quantum mechanical operators and also of the canonically conjugate operators. From there, we also learned the time evolution of quantum mechanical state vectors, and for doing this, we used the time-dependent Schrodinger equation. And then, finally, we learned some important properties of representations, basis of Ket and Bra state vectors, and unitary matrices. And not only some important properties, but we also learned about some identities which are concerning the representations, the basis of Ket and Bra state vectors, and the unitary matrices. And we also learned how to prove these identities. Thank you.